Welcome. This presentation will be about multi-body model simulating biodynamic response of the seated human under whole body vibration, prepared by Maciejewski, Błażejewski, Pecolt and Królikowski, from Koszalin University of Technology in Poland. The presentation will proceed in the following order. At first, a brief introduction and purpose of the research will be presented, then simulation model of the seated human body will be discussed together with identification its parameters. Then model verification will be shown by using laboratory's evaluation of the human vibration. Finally, the brief conclusions will be announced. In order to develop biomechanical model of the human body, at first the model structure has to be specified and then the model parameters must be identified. Biomechanical models should meet the average subject's anthropometric characteristics that represent the human population. Human anthropometric data, including masses and moments of inertia for the human body parts, are typically obtained during the medical examination of corpses, whereas the anthropometric data of individual body segments are widely discussed. In this paper, the anthropometric data for a standard male subject of the average height and body weight is considered for the purpose of evaluating the human exposure to mechanical vibration. Currently, biomechanical models of the human body are becoming more and more useful in modeling of seating dynamics. An opportunity of creating more complex and accurate models provides for studying the vibration influence on humans on much larger scale than time-consuming laboratories tests. Over the last 30 years, researchers have developed a large number of biomechanical models, ranging from simple ones such as 1 or few degrees of freedom to very complex ones, containing from several to several dozen degrees of freedom. The uniaxial models are often and willingly used in many research and evaluation studies due to their functional advantages. An application of such models allows for the useful evaluation of vibration with respect to human response. The proposed multi-degree of freedom model simulating biodynamic response of the seated human body is shown in this figure. Such a model consists of 3 interconnected masses by using linear springs and dampers. The first mass M1 represents the human pelvis that is in contact with the seat cushion by means of viscoelastic elements. Their stiffness CSI and damping DSI coefficients, I equals X, Y, Z, are specified for different directions of the vibration exposure, that is, longitudinal X direction, lateral Y direction and vertical Z direction. The displacements QSX, QSY and QSZ are considered as model inputs that generate the seat vibration transmitted to various body segments. The second mass M2 simulates the human torso that is in contact with the backrest of stiffness C2SX and damping D2SX. In this case, the seat vibration are transmitted to the human body along the x-axis, while vibrations of the torso in other orthogonal directions are induced by internal springs and dampers of the equivalent stiffness C21I, C32I and damping D21I, D32I coefficients, I equals X, Y, Z. The third mass M3 represents the human head that has no contact with the backrest. However, the head oscillations along Y direction are stabilized by the damper, SKY, suspended in the inertial reference point, skyhook damper control. The first equation is the equation of motion for the suspension system under study in terms of the equilibrium condition of the forces acting in the system, where m is the mass of vibro-isolated object, x is its longitudinal displacement, Fcx is the tension spring reaction force, Fbx is the reaction force of end-stop buffers, Fdx is the damping force of a shock absorber, Ffx is the friction force resulting from the relative motion of a suspension mechanism. The second equation is the reaction force of 2 tension springs defined just by the linear function, because of such system components demonstrate a linear force increase as a function of the suspension deflection, where K is the equivalent spring stiffness, is the relative displacement of horizontal suspension system. Third one represent the force of end-stop buffers by the polynomial approximation of measurement results that are obtained during a quasi-static test of the seat suspension system, where xb defines the free stroke of a suspension mechanism without the contact with end-stop buffers, A, B and C are constants that define coefficients of the cubic equation. The first two conditions take place when the relative displacement of suspension system is higher than the free stroke xb in negative direction. The last one is applied in the free range of suspension stroke when the vibro-isolated object has no contact with any buffer. Mathematical model of the shock absorber, equation 4, is also given as the nonlinear relationship between the damper force and its relative velocity, where is the relative velocity of suspension system. A, B and C are the coefficients of approximation function that are identified by means of experimental testing. The final equation describing the friction force generated by moving parts of a suspension mechanism, which is determined as a function of the relative velocity and is assumed to be divided for two different states of motion. The first state is responsible for low velocity motion static friction, and the second one is activated when the suspension system is in motion kinetic friction over a specific velocity, where FFS and FFK are the measured values of static and kinetic friction force, respectively. The function marked as y describes the hysteresis behavior of the kinetic friction force and is calculated by using the algorithm showed below. Equation where is the turning point of a hysteresis, which corresponds to the specific location where the system starts moving in opposite direction. The value delta y with star defines the previous value of y until the turning point is reached. Last indicator is the saturation slope of the continuous transition, which is determined by the parameter. If the displacement qs and the velocity qc are treated as input vibration to the system, then the input vector together with the equivalent input matrix are determined as follows. Acceleration signals of the human pelvis q1i, torso q2i and head q3i are selected as measured outputs, thus the output vector is described in the following way. The resultant output matrix for calculating the accelerations of particular human body parts is expressed as, under the assumption that the system inputs do not affect the system outputs directly and therefore the feed-through matrix D is the zero matrix. The tested person is exposed to whole body vibration in sitting position when the cushioned seat is occupied and the backrest contact is provided. The acceleration signals acquired from 3 linear accelerometers are used for evaluating biodynamic response of the seated human subjected to random vibration. The time history of the acceleration signal applied for different directions of the vibration exposure, I equals x, y, z, is presented in figure, and its power spectral density, PSD, is demonstrated in Fig. P. In order to evaluate unknown parameters of the model, the transmissibility function is used to evaluate the dynamic response of human body parts in the frequency domain. When the transmissibility magnitude is high, it means substantial vibration is transferred to a given part of the human body from seat base. This function is calculated by using the following relation, where CSD is the cross-spectral density of two distinct signals, the acceleration of input vibration and the acceleration, measured at a given body part, that is pelvis, J equals 1, torso, J equals 2, head, J equals 3, that are determined along specific axis of the coordinate system, I equals x, y, z. PSD is the power spectral density of the input acceleration, F is the frequency in hertz. The proposed identification method minimizes the error between numerically simulated and experimentally measured transmissibility functions over the frequency range of 112 Hz. For that reason the root mean square error, RMSE, is formulated in such a way, where, under the transmissibility functions obtained by means of numerical simulations and laboratories measurements, respectively, assuming averaged masses of the particular human body parts, pelvis M1 equals 25, 18 kg, torso M2 equals 46, 77 kg, head M3 equals 8, 04 kg. The error minimization process involves the decision variables describing visco elastic characteristics of the biomechanical model. In order to find the minimum of the objective function, the gradient method is used. This method is implemented in the MATLAB registered sign Software is the Fminkin function. The nonlinear programming solver is used for minimizing the multivariable function, k11, that is constrained by the set of lower and upper bounds. The initial conditions play extremely important role for the gradient methods, therefore the proposed optimization is realized 10 times using the randomly generated starting points. Such a procedure guarantees finding model parameters that correspond to the global optimum of the objective function. In this table, optimal design parameters of the human body model are presented that are specified for particular directions of the vibration exposure. As is shown in this table, there are 3 different sets of the stiffness and damping coefficients that are applicable to the model for simulating dynamics of the seated human body under whole body vibration. As follows from this fig, the simplified model can well represent biodynamic response of the seated human body, however the resulting model inaccuracies are observed for different directions I equals x, y, z, of the vibration exposure. The simulation and measurement results for longitudinal x direction are compared in figure where to local maxima of the transmissibility function, the first maximum around 2 Hz and the second around 3 Hz, are recognized in case of head measurements. While the model shows only one maximum exactly between these frequencies, that is approximately about 2.5 Hz. Moreover, the head vibration transmission responses for the frequencies above 6 Hz are higher in comparison with actual measurements executed in laboratories. Although a small shift in resonance frequency, approximately 0.5 Hz, of the torso is noticed, the simulated and measured transmissibility behavior of torso and pelvis are comparable at higher vibration frequencies. The greatest discrepancy is shown for the pelvis exposed to vibration measured along the translational y-axis, Fig B. About the second resonant frequency of 5 Hz, unexpected vibrations with a too high amplitude are achieved by using the simulation model, and also the proposed human body model gives slightly lower vibration levels than the measured subject at higher frequency range, above 7 Hz. In contrast to horizontal vibrations, very good agreement is observed between measurements and simulations in vertical Z direction. As shown in Fig C, the vibration transmission characteristics for each human body part are well correlated in the whole frequency range, that is at frequencies from 1 to 12 Hz. Nevertheless, for each individual axis, I equals x, y, z, the simplified model can well represent the biomechanical behavior of head, which is the most important part of the human body. In this paper, an unconventional methodology for creating a simple 3-mass model is proposed in order to reproduce and study the biodynamic response of seated human subjects exposed to whole body vibration. The recommended model structure is greatly simplified. However, it reproduces quite well the vibration transmissibility behavior of the human body. Although the masses of individual human body parts are defined a priori based on literature studies, the unknown model parameters, that is stiffnesses and damping coefficients, are identified by using the optimization procedure that minimizes the root mean square error, RMSE, between simulation and measurement results. The model, including Skyhook damper, effectively deals with stabilizing the head while the human body is exposed to lateral vibration in Y direction. Therefore, the presented model can be fully exploited for simulation purposes, and its use leads to fast response time with low computational costs. Thank you for your attention.